Hi guys. So today is really an introduction to irrational functions, and then we're also going to review discontinuities that we looked at back in first semester. So to start, we're just going to review the different types of discontinuities. So looking at this first function, that function actually is not discontinuous. It is continuous everywhere. And in that graph, you should recognize that's a polynomial. And actually, all polynomials are continuous on their entire domain. So that means all quadratics, cubics, linear functions, and then any variation of a polynomial is going to be continuous everywhere. Absolute value is also going to be continuous everywhere. Exponential functions are continuous everywhere. Square roots are continuous as long as it's in its domain. There's a few others. The most common discontinuities are going to occur in rational functions, which is what we're going to start looking at. So two of those discontinuities we talked about. One was an infinite discontinuity, or we sometimes just said a vertical asymptote. Now, when we talk about where a function is discontinuous, we list the x value. So this function is discontinuous at x equals 0, and it's because it has that vertical asymptote. The way you can tell it's an asymptote is because your graph, as it gets close to that value, is approaching either positive or negative infinity. The next one, that's an example of a removable discontinuity or whole. And the reason that this one is different is because one thing you'll notice, both sides of your graph are still approaching that same y value where your graph is discontinuous. It just happens to be a hole there. It'd be possible to fill in that hole and actually make that graph continuous. Whereas on a vertical asymptote, doesn't matter where I put a point, it's still not going to be a continuous graph. Same thing with that jump discontinuity. Wherever I want to put a point, it won't matter. That graph is still not going to be continuous even if I put a point right here. This one's going to be something that comes back up when you get into calculus, because you'll talk about how at that value where that hole is, the limit actually still exists because both sides are still approaching that same y value. But the function's just not continuous at that point because it's not defined at that point with the same y value as a limit. But you'll get way into that more once you guys get into calculus. The last type of discontinuity is a jump or a break. These happen most often in piecewise functions. So if you remember piecewise functions, it's a certain function on a certain domain, and this function is discontinuous at x equals -1. And again, your left side and right side are approaching different values. So with an asymptote, they were approaching either positive or negative infinity. With a jump or a break, they're just approaching different y values. With a removable, they're approaching the same y value. So now let's look at some equations. So we're just going to talk about at a specific point. So if you look at this first point, or this first graph, when x equals 2, well, x cubed plus 1 is a polynomial. Polynomials are continuous everywhere, so yes, this graph is continuous. We also know if I plug it in, I'm going to get a y value. It's going to be defined. Nothing crazy is happening on that graph. But now let's look at b. Okay, this is a rational function. Now, on Friday, when we look more at rational functions, you guys are going to understand more of what type of discontinuity this is. But for now, I just want you to see, if I were to plug in 2, I would get -1 divided by 0. Well, that's not defined. And if my graph is not defined at that point, there's no way it can be continuous at that point. Now, the type of discontinuity, again, we're going to spend more time on this on Friday when we get into more of the pieces of rational functions, but that is going to be a vertical asymptote. All right, the last two are piecewise functions. Now, if you remember, piecewise functions are a certain function within a certain domain. So just a rough sketch of this graph. When x is greater than 3, I have a line with a positive slope. When x is less than 3, I have a line with a negative slope. So my graph's going to look something like this. The question is, do these two pieces meet up? So if you remember, some piecewise functions, we had that open circle and that filled in circle, whereas with some piecewise functions, that filled in circle overlapped, and that created a continuous function. So what we need to figure out is, do these pieces overlap at x equals 3? Well, let's check the left side of this graph. The left side of this graph is when x is less than 3. Now, it will actually equal that point. That means I would have a filled-in circle at -4. The right side of this graph, when x is greater than 3, is going to get really close to the value of 1. So we'd have an open circle when y is 1. So 3, 1 would be an open circle, and 3, -4 would be a filled-in circle. Well, those are different y values, which means my graph, if I want to actually sketch it out, is going to look something like this. And that is going to be a jump discontinuity. So no, this graph is not continuous. It's a jump or a break. Well, now let's look at D, and let's talk about at x equals 5. It should say that specifically since we're talking about a point. Well, same thing. This graph is going to have two different functions approaching 5. Well, let's see what happens on the left side. If I plug it in when x is less than, I get 9. So I'd have a filled-in circle at 5, 9. Then we look at the right side, I plug it in. I also get 9. So it'd be an open circle at 5, 9. Well, that filled-in circle is going to fill in the open circle, so this graph would be continuous for its whole domain. What that graph would look like is kind of you'd have your parabola, and then branching off that parabola, you'd have that line. All right, so one other one, let's go back to that previous example, and let's say instead of x equals 3, we were saying x equals 2. Well, even though this graph is not continuous at 3, this graph is continuous at 2. Again, go back to your picture. 3 is where we had the jump or the break. There's no other jumps or breaks in the graph. At 2, that's just a point on my line. Because the reason that matters, it's only in the domain of the bottom function. That top function has no effect on the graph when x equals 2. So the only place these piecewise functions could be discontinuous are the intervals where these meet up. Now, it is possible to have a removable discontinuity on these graphs. One example would be for example, on D, if instead of less than or equal to, that was just less than 5. That would be a removable discontinuity because now you would have an open circle at that point for both of those graphs where they meet up. And they both approach that value, so that would be a removable discontinuity. Another option, we saw some of these way earlier in the year, but when you had functions where it was like x equals 2 and x doesn't equal 2. There was only one spot where it wasn't that, so you had that open circle, and then, on this function you had an open circle with a filled-in circle. So that's another case where the piecewise can give you a removable discontinuity. All right, so now we're going to transition and we're going to start looking at the rational parent function. Now today, we're really just going to get into an introduction. We're going to look at some of the pieces, some of the characteristics, and we're going to look at transformations. Now, kind of similar to polynomials, we're going to look at transformations today, but the transformations for this function are not the most frequently used way to graph these rational functions. We're going to look at a more detailed approach to graphing rational functions on Friday, because today it's really only going to help us graph the simplest rational functions. And the more complex rational functions come up a lot more often, so we're going to use the process on Friday a lot more than we use this one. So a rational function, think about a rational number. A rational number can be written as a fraction. A rational function is a fraction, but specifically it's a polynomial divided by a polynomial. Remember, a single number is a polynomial. So like 3 over x squared could be a rational function. What is not a rational function? 2 to the x is not a rational function. So you will not see that as it's not a polynomial. 2 to the x is not a polynomial, so you won't see that in part of a rational function. The square root of x is not a polynomial. Let's see, we talked about x to the 3/4. You have to have whole numbers. Another one that is not a polynomial would be the absolute value of x. Because if you remember, we said those polynomial graphs don't have any sharp turns. So that absolute value comes to that sharp point. It's not a polynomial. Those polynomials always had those nice smooth curves on them. So polynomials are, your quadratics, your linears, and then, any other combination of just your basic normal terms. That could be the denominator or numerator for a rational function. All right, so let's look at what the rational parent function looks like. So we'll start by plugging in some points. So I'm going to start by plugging in 0. Well, if I plug in 0, my graph is undefined. So I don't know what that tells me. So what I need to do is figure out what's happening close to 0. So I'm going to start by picking some points and seeing what happens as I get closer to 0 from the right side. Well, if I plug in 1, I'm going to get 1. Okay, well now let's get closer to 0. Let's try like 0.0, or let's do 0.1. 1 divided by 0.1, that's like 1 divided by 1/10. That gives me 10. All right, well, let's get closer to 0. Let's do 0.01. 1/100th. 1 divided by 1 over 100 is 100. Let's do 0.001. That would be 1 over 1,000, which is 1,000. So those x's that I'm picking are getting closer and closer and closer to 0. And as I get closer and closer and closer to 0, those y values are getting bigger and bigger and bigger and bigger and bigger. But they're never actually going to touch 0 because my graph is undefined because I can't touch 0. So that's showing us the right side of 0. Well, now let's look at the left side. All right, let's start with -1. Well, 1 divided by -1 is just -1. Well, then let's get closer to 0. Let's do a -0.1, -1/10. So 1 divided by -1/10 is -10. Then let's do the same thing, -0.01. That would be -100. -0.001, -1,000. So as I get closer and closer to 0, those y's are again getting smaller and smaller and smaller. And that is how I know that there's an asymptote at 0, because my graph is approaching infinity. Now, it doesn't matter that one's approaching infinity positive and one's approaching negative. They could go in the same direction. They could go backwards. We'll look at transformations and some things today and on Friday so you can see how those change. But what matters is that as your graph gets closer to that asymptote, the y's are going towards infinity. All right, so now let's talk about the end of this graph. All right, so let's talk about as my x's are getting infinitely bigger, what's happening to my y's? Well, if I plug in 1, it's 1. If I plug in 2, it's 1/2. 3 is 1/3, 1/4, 1/5. So those fractions are getting smaller and smaller and smaller. If I keep going, I'd have 1/10, 1/100th, 1/1000th, 1/1,000,000th. Those fractions continue to just get smaller and smaller and smaller, and they get closer and closer to 0. They don't actually touch 0, but they get closer and closer to it. All right, let's look at the negative side. Again, -2 would be a -1/2, -1/3, -1/4, -1/5, -1/6, -1/10th, -1/100th, -1, you see the pattern. Again, getting smaller and smaller and smaller, but not quite getting to 0, just getting closer and closer to it. So that shows us that we have a horizontal asymptote on this graph. So that horizontal asymptote shows the end behavior of your graph. So vertical asymptotes occur because we can't divide by 0. You actually cannot touch that point. So you will never touch or cross. So again, we can't divide by 0, so that's why we have that vertical asymptote that you can't touch. Horizontal asymptotes are different. Now, the ones we look at today, most of your graphs are going to have a similar kind of shape to them. But as I said, when we get into the more complex graphs on Friday and next week, you're going to start to see some very different things happening with these graphs. And because the horizontal asymptote is just showing our end behavior, it's not something that you physically can't touch. So you actually can touch and cross a horizontal asymptote. So we'll see more examples of that on Friday. All right, so now let's just go back and review all of our vocab, domain, range, and all these other intervals. Domain here looks a little bit different. So left to right, -infinity, then it stops. It does not touch that vertical asymptote. Then it continues, and then it keeps going to infinity. Range is bottom to top, so our lowest y value is -infinity. It keeps going until the y value of 0. It picks back up at 0, and then it keeps going until infinity. Increasing intervals. Well, let's look at our graph. So as our x's get bigger, well, that first section of the graph, my y's are getting smaller. That second section of my graph, my y's are also getting smaller. So this graph is actually decreasing everywhere. Now, we're going to write it as 2 intervals because at 0, nothing's happening, and it's not decreasing from -1 to 1. So we just write those 2 separate intervals. And this graph does not have any increasing intervals. If you remember, positive intervals, that is where we list the x's where our y's are positive. So this interval right here is where my graph is positive. So that is from -infinity. That is from 0 to infinity. Negative intervals would be when, again, my y values are negative. So to list that interval, that would be from -infinity to to 0. Symmetry on this graph, this is actually an odd function. Remember, algebraically, if I evaluate f of negative x, I get a negative 1 over x, which is negative f of x. So this is an odd function, which means it has origin symmetry. Asymptotes we already talked about. This graph has a vertical asymptote at x equals 0. And there is a horizontal asymptote at y equals 0. Now, whenever you write your asymptotes, you need to make sure that you write them as lines. They are equations of lines. So we do need to say x equals for vertical, y equals for horizontal. All right, end behavior, a little bit different than what we've seen so far. So as x approaches negative infinity, let's see what y approaches. Well, as my x's get smaller and smaller, my y's are actually approaching the horizontal asymptote, which is 0. As x approaches positive infinity, it's the same thing. My y's are approaching that horizontal asymptote, which is 0. Now, in addition to end behavior, we're going to look at something else. And this isn't really the end behavior of the graph, but we do want to kind of talk about what's happening here and here. The reason we kind of want to start looking at that is really end behavior is getting you guys ready to write limits when you get into calculus. And while this isn't an end behavior, it is something you'll probably see once you get into limits. So what we're going to look at is what happens as x approaches that vertical asymptote. The problem is it's approaching two different values based on what side of the graph you're looking at. So we can specify which side we're talking about by putting a little plus or a little minus up there in the corner. That little plus means as x approaches 0 from the right side. So if I look at the right side of 0, well, the right side of that graph, as I get closer to 0, is approaching positive infinity. Then I can look as x approaches 0, I could put a little negative, that means the left side of my graph. Well, the left side of 0, as I get closer to 0, those values are again getting smaller. So y is approaching negative infinity. All right, so now what we're going to do is we're just going to look at some basic transformations. Again, we're going to keep these pretty simple today. The way we graph these functions today is going to be different than the way we're going to graph these in the coming days, because the ones we look at in coming days are going to be a little bit more complex than these. So transformations, remember, if it's near the x, it's horizontal. So x plus 2 is going left 2. Minus 3, that's your vertical, that's going down 3. So when this shifts the graph, it's also going to shift the asymptotes. So my vertical asymptote is going to shift left to x equals negative 2. And if you think about it, that value makes sense. Because if I plug in negative 2 for x, I'm dividing by 0, which I can't do, which is why there's an asymptote at that point. Horizontal asymptote, that's also shifted down. So I get y equals negative 3. Now, this graph is going to have the same shape as the parent function. So it is, when it comes to sketching these rational functions, the specific points are not nearly as important as if the asymptotes are correct, the intercepts are correct, and then that we have our graph drawn in the appropriate places in relation to those asymptotes. So kind of similar to polynomials, where kind of what was happening in here wasn't as important as what's happening at your intercepts and what's happening kind of near those asymptotes. So to help us with that, the Schoology notes had this already placed on there, but I didn't edit this page. We're going to also look at the y-intercept. So to find the y-intercept, for every function we ever look at, you replace x with 0. Well, if I replace x with 0, then I get 1/2 minus 3, which is a negative 2.5. So my y-intercept is 0, negative 2.5. That also helps us see where our graph is going to go. So typically the way these graphs kind of work out, if you notice, there's kind of like 4 quadrants here. And we kind of need to figure out which quadrant our graph is going to go in. And we'll look at this again a lot more on Friday. But for now, the shape is going to be similar to the parent function. The parent function had one curve kind of here in the top right, and then it had another curve down here in the bottom left. Now, again, the specific points like around here are not as important. We need to make sure our intercepts are accurate and that we've drawn these curves in the right places. The other important part, again, is the asymptotes. That's a really important part of this graph. All right, so now let's look at the domain. So again, this domain, it's restricted by the vertical asymptote. So vertical asymptote will restrict the domain in our graph. Range will also restrict the domain in our graph. I'm sorry, I just said range. Holes will restrict the domain on our graph. The holes, when we find those, will restrict domain. Range, actually today, range is really only going to be affected by the horizontal asymptote, but once we get into these more complex graphs, range is going to be very, very different. So we can't really rely on this same kind of pattern. All right, so now we're going to look at what happens as x approaches -2, and that little plus means from the right side. So I look at -2, and then I look at the right side. So as that graph gets closer to -2 on that side, my y's are approaching infinity. All right, let's look at our next one. Transformations, this graph has gone right 4, up 2, and it has been reflected over the x-axis. So that means the shape of this graph is going to look different. Now, one thing that is nice about these, if I reflect this graph over the x, or if I reflect it over the y, it's going to look the same. So whether or not you flip those, it's actually going to still work out. Because of those transformations, vertical asymptote is x equals 4, horizontal asymptote is y equals 2. And again, because it's reflected, it's going to go in these quadrants. Your intercepts will also help guide you to that. We'll talk on Friday about how to find the x-intercept, but for today, to find the y-intercept, if I plug in 0, that's a negative 1/4 plus 2, so that's 2 1/4. And then again, that fits with where I drew my graph in relation to those asymptotes. Domain is -infinity to 4, and then 4 to infinity. Range, -infinity to 2, and then 2 to infinity. Then we look as x approaches -infinity. Well, as our x's get smaller, our y's are approaching 2, which is the horizontal asymptote. All right, so the last two that we're going to look at is we're just going to look at a function that looks more like the format we're going to see on Friday, but again, they'll be a little bit more complicated. But this is a pretty basic rational function still, but what we can do is by using division, we can actually rewrite this into the form we just saw in order to see those transformations a little bit clearer. Because if you think about it, division, okay, and that fraction bar kind of mean the same thing. So I can do 3x minus 2 divided by x plus 4. Well, since it's x plus 4, I can use synthetic division. And if you remember, the way we write our answer for synthetic division, we start 1 degree less. So 1 degree less than 3x is just 3. And then we write the remainder as a fraction over the divisor. Well, now this is in a format pretty similar to what we just did. Now, this is not the way we are going to graph these functions going forward. Okay, this is just, I want you guys to kind of see how it corresponds to division and just understanding, again, those transformations. But we are going to graph this using a different process come Friday. The reason we're going to do that is because this process does work well when you have kind of a linear function in both the numerator and the denominator. But when you get into quadratics and cubics and higher order functions, this process doesn't really make it much easier to graph. All right, but using this, we can now see that we have a vertical asymptote at -4. Horizontal asymptote at y equals 3. This graph has been reflected, so it is kind of going to be in these quadrants. But let's go ahead and get our y-intercept. Y-intercept is way easier from the original. If I just plug in 0 top and bottom, I'm left with -1/2. So I can see there's my y-intercept. So I'm going to have one curve in this box and one curve in this box. All right, let's go ahead and look at this last one. We'll do our synthetic division. The remainder, again, we write as a fraction over the divisor. So our vertical asymptote would be at 3. Horizontal asymptote would be at -2. That graph's been reflected. And then let me go ahead and write the y-intercept. I didn't go through it pretty close, but if I plugged that y-intercept in, I would get 1/3 as a y-intercept. That would give me another accurate point. All right, so the last thing I want to show you guys is just how that vertical stretch, whenever we look at this, actually affects that graph. You'll notice whenever we graph these, by changing your intercepts, that's going to you'll see that effect pretty clearly. But I do want you guys just to see an example here on Desmos of how adjusting that stretch actually makes the graph look. Okay, so right here you guys can see, here's your rational parent function, As I move h, okay, that's changing my vertical asymptote. As I move that k, it's changing my horizontal asymptote. Now notice, again, typically we're not going to see this outside value whenever we get to the rational functions we'll see later on. Typically it'll all be just one numerator and one denominator. But again, I wanted you guys to see how it affects it. Well, now let's look at that a value, that stretch. As I make it bigger, you'll notice what it's doing is it's stretching it away from really that intersection of those asymptotes and pushing it farther away. When a becomes negative, it reflects, and again, as it's larger, it is stretching that graph farther away from where those asymptotes intersect, and that's what that stretch is going to look like. Now, for the sake of what we're doing in here, what's important is that you get the accurate intercepts. I'm not going to be as concerned about getting all of these little points in here correct and how the difference between them is. By getting your intercepts correct, that will make it clear how your graph has changed compared to some other graphs. And notice as we change this, it changes your intercepts, okay? All right, so that is it for rational functions. We will look at, again, like we said, some more complex examples on Friday.